Right, friends, internet. What we have here today is a resolver. So I've taken off this top cover. So that means we can take out the rotor and examine that. So here's your primary. And there's the two wires from the primary going to the secondary. So that's one winding over there. Okay. And you can actually see the poles. 6 poles, I think. Bit difficult to see them. And then inside stator there's 2 secondaries, a sine and a cosine. But we'll be able to work out from the, when we turn it, how many poles it's got by looking at the scope which I've got set up over there. And I've got a cam for you guys watching the scope. So this fits over here like that, and the rotor sits inside it. So we are going to leave the rotor inside there like that, and it's going to spin on the back bearing. Oh, very good. Now we need to identify the top winding. Let me show you. So this couples with that winding over here. That's your primary, that's your excitation. So that's your primary, your excitation, and your 2 secondaries below it. Alright, primary, secondaries. So you got windings on the rotor and 3 windings on the stator, hence you got 6 wires. So here's your rotating winding. So this is a nicely built rotor. You can see exactly what's going on there. It's a very nice illustration of a resolver. This is a resolver used for position feedback. And it's obviously an absolute position feedback device. So now we need to identify over here the excitation and sine and cosine secondaries. So we're going to fire up the meter. Yeah, you can see it. We've got 100 ohms. And then we've got another winding. 300 ohms, 336. And another winding, 336. Okay. So your 2 secondaries are going to be the same value in resistance. That means the 2 336 ohm windings are your secondaries, and the 100 ohm winding is your primary. They generally don't have the same ratio. There's either a 1:2 or the 1:3 ratio on resolvers. So now we know that we're going to take our signal generator over here and hook it up to the primary like that. Okay, you can see what I'm doing on the, I'm trying to keep things in frame here. Then we're going to take our 2 scope probes and to take channel A and connect it like so, and take channel B and connect it to the other one. Alright, now what we need to do is just set those voltages down a little bit. So I'll set them to 3 volts. I'm going to slow the scope down, and I'm going to bring up the excitation. I've got that set to about 700 kilohertz. Move our trigger up. Turn channel A on. Okay. Now we are triggering on yellow. So let's put that over there. So we've got a good trigger there. Yeah, that's reasonable. I've got the signal generator set about halfway up. So as I spin this, the amplitude between these two changes. So there they're in phase. Like that. So let's call that 0 degrees. Alright. There they're 180 degrees out of phase. Now what we can do is look at the shaft. Let's go back to 0 degrees. That was a fairly small movement. So let's go back to, so that's over there. And then we go to 180 degrees. That's a very small movement. That's a very small movement indeed. So this has got lots of poles. So it's a fairly high resolution resolver this. So there we drop it back in. Now we're in 180 degrees out of phase. 90. Call it 270. 0. That would be 90 degrees. So there we got nothing on that one. There on that one. So from a yellow line being flat over there to the blue line being flat, and that is about, it went from 6 o'clock to about between 3 and 4 o'clock. So that's probably about 40 degrees. Turn a bit more. Yeah. So it's not quite 90 degrees. Maybe call it 60. Suppose that's going to divide. 6 times 60 is 360, so that's 6 poles. So that would tie up with this being suited to a 6-pole servo motor as a feedback device. Okay, there we have it. Very good. So if I turn that a further 120 degrees, yep. So there we're at 12 o'clock now. Alrighty. So there you can clearly see the relationship between the two phases changing as I turn the shaft. So that relationship over there will tell the position controller or the drive what this angle over here is. So that's how a resolver works. If you are testing a resolver, this is typically what you do. You put I have got let's measure the frequency. Add measure. Where is it? Measure. We want horizontal. We want frequency. Yeah, 750 Hertz. There we go. Yes, you guys can see that all right. 750 Hertz. So if I change the frequency on the signal generator, you can see it just changes on the resolver. Alright. But the behavior of the resolver still behaves the same. Okay. So a resolver is basically a transformer. You got magnetic coupling. Okay. Your excitation over here, which is what my frequency generator is connected to, the primary winding, through these two rings, it couples to that winding over there. Alright, that winding is electrically connected with these wires to this secondary over here, which is 6 poles. Alright, as we thought initially, 6 poles. That couples down there with two windings which are 90 degrees out of phase. Your sine and your cosine winding, okay? Sine and cosine, they're 90 degrees out of phase. And gives us the two signals on the scope like that. Which then provide us with an indication of the rotor position. Now, let's talk about resolvers and why they were so great initially. It's because this over here is vibration resistant, it's temperature resistant, they don't degrade as long as the bearings hold up. There's nothing to wear up. There's no moving parts in them. Okay. They're easy to manufacture. They're slightly on the heavy side. It weighs a bit more than encoder. Of course, there's a lot of metal in it. But to this day, they're one of your most robust and reliable feedback devices. That's why they're still used on aircraft for position feedback. Because they're pretty much guaranteed to never fail. They're one of the best feedback devices ever devised. Okay, so that's why aircraft still use them. They use resolvers because they don't fail. And in terms of integrity, you can over here easily see if a wire is broken, because you no longer get anything out from it. Okay, same for the blue. If you get a wire break, the blue goes straight and you know you've got a problem. Also, your controller can check that it's finding the resistance of the winding. So there's a lot of safeguards that you can build in which are very effective. The other thing is that the output signal coming from this is very immune to electrical interference. It's a fairly low impedance circuit, therefore you don't easily get induced voltage into the circuit and interference. Alright, also good, very good. Right, so it has an AC source powering it, so you need to supply it with power. So if I change the signal generator's output to a triangular wave, let's slow it down a little bit. like that. Let's go to square wave. You can see that appear on the output as well, like that. Right. Now obviously this is designed to work with a sine wave, so you're getting a bit of distortion when you're not applying a pure sine wave. So we go back to pure sine wave and it looks like that. Now depending on how fast this thing has got to do that, you excite it with your AC input. Okay, currently we're running at about 2 kilohertz, but I think that they go even higher, like about 6 kilohertz, when this thing needs to show that the voltage back to the controller fairly rapidly. So if we turn this right down, you can actually see the movement on the scope as I'm turning it there. So that's what your controller actually sees, and the AC in the background is the excitation. Alright, so if I increase this, that's what it looks like normally. It's fast. Alright, so that's what happens under normal circumstances. You see the two shifting like that. You can see it beautifully there on the scope. There's your position feedback. Alright, beautiful. Very good. This is working very nicely. There's a little bit of movement in the resolver, but that's working nicely despite it being able to move in there. As you can see, it's not affected by vibration. It's really great device. I rescued this out of the trash about 2 years ago and I put it in the cupboard at work, and today I'm digging in there for some test equipment and I found this and I thought, heck, perfect opportunity to make a really nice video about resolvers. Let me take it home, I'll hook it up, pop the lid off so that you can see what is inside, and we'll examine it together. And there you have it, just like that. That's a resolver. There's not a lot more to talk about with resolvers. This is obviously a two-phase output. Okay, so there's your two phases that shift like that. So that over there, that's your 90-degree shift, or 60 degrees, like so. Yeah, for more resolution you could have, you could have 3-phase out, then you'd have 120 degrees between phases. But generally resolvers have two secondaries, which are sine and cosine. That's it. They use them in aircraft, they used in marine. The up on top for the wind vane, they generally use these on top of the mast, or they certainly did. I think to this day they still use them. Of course, it's very, very robust. If you were to get salt water into this, it's not going to instantly destroy it. in fact the electronics is going to keep on working until the iron corrodes and it seizes up. With an encoder you'll be in trouble far sooner. Salt water or some other liquid that's got into the encoder, it's over soon because they're optical. And you got to keep them clean and you got to treat them with care. It's a whole different animal. Right, I think we are done here. This was a lovely talk. Thanks for joining me here. Hope you enjoyed it. I hope you learned something. Those of you who don't know too much about resolvers, I hope I explained it well enough. And for the rest, take care. Then also no further. And I'll see you next time for more stuff. Thank you, ladies and gentlemen. Bye.